Okay. So today, as we were discussing about cryptanalysis, so we will continue with cryptanalysis of modern block ciphers. And last test class we had seen a method which was named as linear cryptanalysis. Okay, so it was supposed to find out linear approximations of ciphers, which also has nonlinear components. Okay, so in today's class we will rather see another method. It's called the differential cryptanalysis. So it's supposedly an even more powerful tool than a linear cryptanalysis. Okay, but we will see and understand what is the working principle. So first of all, we will try to understand the concept of differentials, and then define something which is called a propagation ratio. So we will define this particular quantifier and see how to calculate this propagation ratio of a given cipher, and then discuss about the original attack, that actual attack, that is the differential attack. How do we carry forward the differential attack given good propagation ratios? Okay, so we will take them one by one. Some points, this method is quite similar to the linear cryptanalysis method. The main difference, okay, so the keyword is difference actually. So the main difference is that it actually uses the information about the XOR of two inputs and the XOR of the corresponding two outputs. So therefore it uses the actual, so the main difference is in the difference itself. Okay, so therefore you are using the difference to calculate, to find out certain properties of your given cipher. So the XOR essentially here symbolizes the difference of your inputs, as well as so you calculate the differences of the inputs and the differences of the corresponding outputs. Okay, so therefore you take two ciphers. So imagine there are two instances of the cipher. You feed the first instance by a given plain text. You feed the second instance by another plain text. So I call them P and P star. The only property being that P and P star maintain a fixed difference. So therefore P XOR P star is a given fixed value, say a P dash. Okay, and then you get corresponding output cipher text like C and C star. So therefore the idea is that this difference which you obtain in the output, okay, so the idea is that whether it is, so there are some expected values of this difference, and you basically what you do is that you guess some bit of the key and you check whether the output XOR is as expected or not. Okay, so that is a broad idea behind the attack. Okay, so this is a chosen plain text attack, right, not a known plain text attack. Why? Because here you are obtaining plain texts which maintain a fixed difference. Okay, so therefore you are not only you know the plain text, but you are actually choosing the plain text. Okay, and therefore supposedly this is an even more powerful attack compared to the known plain text attack. Okay, that is the linear attack. But therefore this has got from the designers, from the attacker's point of view, there are stronger assumptions, right? The assumption is that you can actually choose the plain text. So therefore again we will go back and look at the algorithm that we cryptanalyzed last day. So we will take the same algorithm as our guinea pig, okay, and continue with our discussion. So therefore if you remember in the last day's class we had been discussing about an SPN cipher which has essentially, which works on LM number of bits, right? So the block length was LM, where L and M are both integers. Okay, so your key is also an LM bit value, and your output is also an LM bit value. Okay, so therefore what you do is that there are NR number of rounds. The first round, I mean the first NR minus 1 rounds. Okay, they say what you do there, you just do a key XORing, and then you continue doing the shift, or rather you continue to do the sub byte the S box operation. Okay, and how many S boxes are there? There are 8 S boxes, or there are M S boxes. Okay, so what you do is that you apply the S boxes, that is the first S box, second S box, and so on till the mth S box, and obtain the corresponding outputs. The outputs are stored in the variable V. Okay, and this particular variable is now essentially storing the output of the S box step. Okay, so what about the next layer? The next layer is a permutation layer. Okay, so what you do there is that you take the LM number of bits and you do a permutation on them, right? So as we discussed, that permutation is nothing but the transposition of the bits. So what you so therefore that you can represent by this particular function called P, and you see that P1, P2 and so on till PLM just represents a transposition of the bits. Okay, so you obtain the corresponding output W, and you do that for say for all the NR minus 1 rounds, and the last round you just do a plain substitution. Okay, therefore there is no permutation in the last round. okay, and then finally you again do a key XORing step. So as I told in the last test class, this step and this step are known as the key whitening steps. Okay. So again a recap at our original the cipher that we were discussing. So we have here essentially we have got L and M, both of them are equal to 4, okay, and NR is also equal to 4. What does it mean? It means that we are operating on 16 bits of values, okay, and there are 4 S boxes, and the number of rounds is also 4. So it is divided into, so therefore this 16 bits is divided into 4 groups, and each of them are of 4 bits, okay. So the S box works on each of the 4 bits, okay. So consider a substitution box. So this is an example of the S box. So therefore since the S box operates on 4-bit values, the inputs can go from 0 to 15, right. Similarly the outputs also. But since we are considering a 1-to-1 S box, that is a bijective S box, therefore both the input and the outputs are just plain permutations of the values from 0 to 15, okay. So it's just a map, okay. So therefore it's a very simple description of the S box. What about the permutation? The permutation means transposition of 16 bits. So you take the entire 16-bit block and you just transpose the bits, okay. So therefore this details how the transposition takes place. So if I implement, for example, in hardware, this will be just a plain hardwiring, right. So you take some wires and you just regroup them, okay. So in pictographically this was how it was looking. So you take a plain text and you obtain a cipher text, and there are key XORing layers in between, which we call as the key mixing layers, and there are 16 bits which we have divided into 4 groups, and each of them are of 4 bits, right. So you again obtain these outputs and you pass them through 4 S boxes, okay. So these S boxes again, after that the output that you obtain from the S boxes, they have to be transposed, right. So therefore this is just a rewiring which you do. It's you can hardwire this part. So it's just transposition. You can see that the first bit comes here, but the second bit goes to the 1, 2, 3, 4 and 5th location, okay. So you can follow that from the permutation table also, that the first bit goes to the first location, the second bit goes to the 5th location, and so on. So you can relate the diagram with this table, okay. So similarly you obtain, there are 4 rounds, and finally you obtain the corresponding cipher text, okay. So this is our guinea pig cipher which has been provided, and today like last day we had performed linear attack on this. Today we will see how a differential attack works on this, right. So this is again now I am considering the problem that is the GPIC cipher secure, but only today I am not concerned with the linear attack. So today I am, as a designer, I am evaluating whether the cipher that I am proposing is secured against a differential attack, okay, or a given chosen plain text attack. Okay, so you remember the key scheduling. So the key scheduling was as follows: you take all the bits and you start from the 4R plus 1 bit position if R is your corresponding round number, okay. So therefore you start, for the first bit you start from here and you collect 16 bits, then again you start from this point and again collect 16 bits, and next round you again start from here and collect 16 bits, okay. So this is a very simple substitution, simple key scheduling technique, okay. So now we start formally what is known as the differential attack, and we start actually informally. So it says that the attacker chooses an input XOR X dash, okay. So therefore you fix an input XOR and I name that to be X dash, okay. So he has several tuples. So for example, he can obtain tuples like X comma X star, where X and X star, if you XOR them, you get the value of X dash, okay. So you obtain the corresponding ciphers from X, that is you obtain the output of, if you encrypt X you obtain Y, and if you encrypt X star you obtain Y star, okay. So for each pair of Y and Y star, he guesses the key value of the last round. So what he does is that he has obtained Y and Y star, which are the corresponding cipher texts. So the last round he guesses some key values, okay, and what he does is that he decrypts the last round. So he decrypts both of the pairs and he checks the XOR at the last but 1 round. So he goes back and he finds out what is the corresponding XOR at the last but 1 round, and he checks out whether the result matches with the most probable outcome, okay. So which he has which has basically found by some probabilistic technique. So therefore we will discuss about the probabilistic method that is to be followed. So based upon this probabilistic approach, if the attacker has first studied the cipher. Okay. So, and based upon his study, he has actually computed that which are the corresponding differentials which are supposed to occur with a large number of probability. Okay. So, with a large probability. So find out, so therefore he checks out whether the result matches with the most probable outcome, which he has found out using some probabilistic approach analogous to the finding of the best linear approximation in case of linear attack. So in case of linear attack, the attacker had previously studied the cipher and had obtained linear approximations of the cipher, right. So in this case actually there is a different strategy. He has performed differential analysis of the cipher, okay, and he has obtained something which is known as more probable differentials in the output. Okay, so therefore, so this is the I think it will become more clear as we proceed. Okay, so therefore, what he does is that he maintains a frequency table for each of the key, noting the number of matches. So therefore, he finds out. So he guesses one key and finds out the number of matches. Okay, and similarly keeps on doing that. It is expected that the candidate key will have the highest number of matches. So that is the broad strategy behind the attack. Okay. So now the next question comes is how do we really carry forward and really obtain those probable differentials. Okay, so therefore suppose in this case we are considering 3 rounds of the cipher. So because there are 4 rounds. Okay, so they exclude the last round, we have 3 rounds, right. So now we are interested in obtaining the output after 3 rounds, which is more probable. Okay, so therefore the idea is this, that is coming back to our diagram. If we set up a differential at this point, okay, I am interested in finding out what differential should occur here with a larger probability. Okay, so therefore I set a differential input here and I am interested in finding out what is the corresponding differential here among all possible differentials which should occur with a large number of probability. Okay, so how do I carry forward in doing this analysis? So we have a reasonably complicated structure, right. So how do we carry forward and do that? So therefore again your problem is mainly the S box. Why? Because apart from the S box, all other layers are linear layers. Okay. So now if I fix an input differential to a linear layer, I can easily predict what should be the corresponding differential at the output of a linear layer. Okay. But the real spoil sport from the point of view of the attacker is again the S box. Okay. So he needs to take care especially for the S box, right. So what he does is this, that is he takes the S box and he does more detailed analysis on the S box. Okay, like we had done for the linear attack, we also had done analysis for the S box. Okay, so in this case also we do analysis for the S box in terms of differentials. Okay, so what he does is as follows. So what you do is that you consider an ordered pair of bit strings of length m. So therefore, suppose your S box operates on m bit values and results in n bit values. So this is an example of an m cross n S box. Okay. So you considered an ordered pair of bit strings of length m, say I call them x comma x star, and I say that the input, that is input XOR, is x XOR with x star. So that is my input differential actually. And what is the output differential? You compute by the value of Sx, you compute the value of Sx star and you take an XOR between them, right. So therefore you obtain y and y star, and that is the output XOR. So note that the XOR is an n bit string, right, because your resultant is finally an n bit value, so your XOR is also an n bit value, right. So now let us define a particular term called delta, and delta is delta x dash. Why do I call them delta x dash? Because I have fixed this value of x XOR x star supposedly. Okay, so that means that x XOR with x star is a fixed value of x dash. Okay, and you obtain all such ordered pairs x comma x star which satisfy the equation that x and x star when taken XOR results in x dash. Okay, so it's called like a differential set. So you form a differential set or a delta set such that, so that is defined to be the set of all ordered pairs x comma x star such that the XOR of x and x star is equal to x dash. Okay, so that is a very simple definition. Okay, so how do I define more? So therefore this is how it looks like formally, right? You take delta x dash is equal to all ordered pairs x comma x XOR with x dash, right, and x you vary from for all the possible m bit values, because that is your the entire space of your x, right. So how many number of elements can you obtain in this fashion? you can obtain 2 power of m values, right? That you, I guess all of us see that there are 2 power of m values in this set, right? The cardinality of this set is 2 power m, right? But how many values, how many distinct values can the output take? It can take 2 power n values, okay? So therefore, this distribution, if I note in the form of a distribution or a table, then this 2 power m output pairs have to be distributed among 2 power n values, correct? So the problem is that if you take a nonlinear S box, then this distribution is actually not uniform, okay? And the attacker exploits this property to mount an attack, okay? So the idea is that if this distribution would have been a uniform distribution, then this wouldn't have worked, okay? But then you will see that it's actually an impossible thing to obtain a fully uniform distribution if you have a nonlinear transformation, okay? So on one hand you do not want nonlinearity, but on the other hand actually nonlinearity is very much required. So you saw that in the previous attack, when we talk about linear cryptanalysis, then we required nonlinearity, right? But in this case we see that because of this distribution's nonlinearity, rather non-uniformity, I am actually mounting an attack, okay? But this doesn't mean that if I replace the S box by a linear transformation, I would have avoided this. No, even then this would have worked, okay?
So by defining delta x dash,
yeah,
are we considering that x star is fixed?
X dash is fixed, okay? So what you do is that x dash is fixed, and then what you do is that you start guessing values of the first element in the pair. So that is x. So how many values of x are there? There are 2 power m values of x. So immediately when you fix x, the second value becomes fixed automatically because x dash is fixed, okay? So that means if you take XOR between these 2 elements in the ordered pair, you obtain x dash, correct? So that is the way how this set has been generated, okay? So that I call as the delta set, right? Is it clear? Okay, so therefore this is an example. I think it will be clear with this example. So you consider this example, say I fix the input differential to 1 0 1 1, okay? So what does it mean? What I do is that how many possible values are there for 4-bit value? There are 16 values, right? So what I start doing is that I start changing the first one like all zeros, then 0 0 0 1 and so on till all ones, okay? Immediately when I fix this one, the second one gets fixed, right? Because your delta is same. So how many possible elements are there in this set? There are 16 elements, okay? And the output is also in this case 16. So it means 16 output pairs have now to be distributed among 16 values, okay? But you observe the distribution, you will find that this is how, so this is for your S box, okay? So therefore this is for the same S box that we have described in the just few slides back. So you take x star, you operate and you operate the S box and you obtain y and y star, and you note the differential y dash. So what is y dash? Y dash is the XOR of y and y star, okay? So now in an uniform distribution, you would have expected that all the values would have occurred once, right? But unfortunately it does not occur. So you will find that there are some values which are completely absent here, and there are some values which are repeated, okay? So there are some output differentials. If you fix the input differential to this, then there are some output differentials which are more expected, okay? And there are some output differentials which are not expected, which are impossible, which cannot occur, okay? So this central idea you will find appear in various kind of cryptanalytic methods, okay? So today we will discuss about differential attacks, but there are other classes of similar kind of attacks also, like something which is called higher order differentials, impossible differentials and so on, okay? And also so therefore this idea is very central. So therefore let's try to understand this properly, okay? So now you can actually obtain a frequency table in this fashion. You will find that, so this is a simple tally table, okay? So it's similar to a frequency table, and you will find that there are certain differentials which have never occurred, and certain differentials which have occurred for quite a significant number of times, okay? So you see that which is the highest number of, or rather which is the output differential which has occurred for the maximum number of times? It is this value, right? So 0 0 1 0 is probably the most expected. So the frequency distribution of the output XOR show that only 5 out of 16 possible XORs occur, okay? The others do not occur. So this is a widely non-uniform distribution that we have. in a uniform distribution all the output XORs would have occurred exactly once, right, because we have a bijective map here. So this so what if the map was not bijective? Then we would have expected in a uniform distribution each of the elements would have occurred 2 to the power of m minus n number of times if m is greater than n, right. So if you have for example for DES your input was 6 bits and your output was 4 bits, right. So if we had a uniform mapping, then each of the elements in a differential table would have occurred 2 to the power of 6 minus 4, that is 2 squared, that is 4 number of times, okay. But unfortunately that does not take place, and therefore you can try differential attacks, okay. So this attack exploits this property which serves as the distinguisher, okay. So therefore this is again you see that the first objective is to identify a proper distinguisher, and it has been proved historically that if you have been able to find out distinguishers, you can convert that into real life attacks, okay. So the first objective of any cryptanalysis is to find out distinguishers. So now you can actually do that for all possible differentials. So same thing, you can do it for all possible differentials and obtain a table which is known as the DDT or difference distribution table, okay. So you see in a difference distribution table what we have noted is in the rows we have given the input differentials, and in the output we have noted the output differentials, and all these are the frequencies, right. See, for example, we had worked out in the previous case the case of b comma 2, right. So b comma 2 was this, that this input differential was equal to b, right, it's b, right, yeah. So and what about the output differential? It is equal to 2. So if I look into this table and I observe the entry at b comma 2, you see b and 2, you get the value 8. So that is what we found out here, right. So that is being stored here. Similarly for the other values also. So you note that there are a lot of zeros, right. So which means that there are a lot of differentials which actually do not take place. So if you fix the input differential to a particular value, then you know that certain differentials which never occur and some differentials which are more expected, okay. So immediately you understand that if you have a table like this, you can also obtain the probabilities, right. So therefore you can find the most probability, least probability, and so on, right. So therefore what you do is this, but before that let us also observe another important thing, that is the key has got no effect on the differential. Why? Now because we are mixing the key by a simple XOR, right, and therefore if you take two such differentials, then the key gets cancelled out. You see that? Okay, so what is your key XORing operation? You take X and you mix the key, right, and you obtain X XOR with K. So what happens in the other instance of the cipher? You take X dash and you mix the same key, right. So what do you obtain? X dash XOR K. So what is the differential here? X XORed with K, XORed with X dash, XORed with K. I can apply my previous properties of the XOR and I can obtain that this is actually equal to X XOR X dash, okay. So this differential here was also X XORed with X dash, right. So therefore if I fix this differential at the input actually passes to the output. So the key has got no effect, right. All of us see that? So if the key was mixed by some other function, okay, say an integer addition, then this wouldn't have been the case, right. But then if we can actually change the definition of the differential and can carry out similar kind of analysis, okay. So my differential is defined as just exactly the opposite of my addition, right. So in this case both of them are XORs because I am doing a GF2 operation. My addition and subtraction both can be implemented using an XOR, okay. But if we had done an integer addition, then we would have defined the differential by subtraction, modulo subtraction, okay. So the key has got no effect on the differential. So the key mixing has got no effect on the XOR because it is mixed using an XOR function which is also used to compute the XOR, okay. So therefore the differential passes, that is the point, okay. So now we can define something which is called a propagation ratio as follows. So propagation ratio or prop ratio is the probability that an input XOR A dash gives a corresponding output B dash. Okay. So we had noted the table, right? So the table essentially had pairs, had elements, had entries at locations which are corresponding to the A dash row and the B dash column, right? So what does it mean? It means that if you set the input differential to A dash, then the number of times B dash occurs in output differential is so on, is say ND A dash comma B dash. Okay. So now what is the probability of the prop ratio? It is this divided by 2 power of m. Okay. So 2 power of m are the number of possible inputs that you can provide. Okay. So therefore you can obtain similar kind of probabilities, and that we may refer to as the propagation ratio or the prop ratio. Okay. So you observe that I think you have, all of us have can say that at this point can appreciate the fact that there are some values for which the propagation ratio will be actually equal to 0 because they never occur. Okay. So now if you have the idea of a propagation ratio similar to something which we have called as a linear trail in our linear attack, we can define something which is called a differential trail. Okay. So what is a differential trail? So it says that since the intermediate keys has got no effect on the XORs, in our analysis we can actually neglect the keys, right? Because they don't have any effect on the differential, right? So you can just simply throw away the keys, and that's actually one reason why differential attack is so powerful. So in the input points, the keys has got no effect. Okay, so if you do a differential attack, the key has got no effect on your analysis. Okay, that makes your analysis quite simple, right? At least simpler. So what we wish to combine is those propagation ratios for which the input XOR of a differential in any round is equal to the output XOR of the last round differential. So what it means is this, that is, so you see that your cipher essentially composes of rounds, like, so idea is that suppose you take round I and you observe round Ri plus 1. Okay. So what you have done is that maybe you have targeted one S box here, okay, and you have targeted another S box here, okay, and you have found out that the propagation ratio of this and this is say high for a particular value. I refer them as say A dash and B dash, okay, and the propagation ratio for this S box is high for say a value of A comma B, okay. So now if I want to combine these two, that means I require to find out the propagation ratio of A and say B dash here, then that means I need to see that this difference is actually influencing this differential here, okay, or is the same differential as this, only then I can combine. You see that? So the moment I fix, say for example I need an A difference here, so that means what? That means for all the other points I fix a zero difference, okay. So now that means if I denote the differential here in a word format, then this would be all zeros followed by A, right? This is the input differential of this round. So now I obtain by my this analysis, suppose I say that in the output you have a large probability that say all zeros and B will occur as a differential, okay. So now after this what do you have? You have a transposition, right? So we will observe that where does this disturbed bits go, okay. See for example these disturbed bits, say one bit goes here, one bit goes here, and so on, right. So the moment, what does it mean? That if there is one disturbed S box, that is actually influencing not one S box but maybe two S boxes, right. So therefore now after you have observed that, you need to find out the difference propagation ratio of this S box as well as this S box, right. So therefore you need to see that the difference propagation which you obtain here is actually equal to the difference propagation here if there was no permutation layer, but if there is a permutation layer, it is equal to the permuted differential, okay. So it is equal, so if your difference propagation here is say delta, I call that delta Ri, okay, so something like this, delta Ri, or rather delta output of Ri, and here it's actually equal, so delta Ri minus 1, and here it's equal to say suppose delta R dash I minus 1, then there, since you have a linear transformation here, you can actually write the delta R dash I minus 1 is equal to the linear function operated upon delta Ri minus 1. So mathematical I can represent this in this format. right. So I mean, this is a mathematical representation, okay, but if you do not bother about this, it just means that it should be such that the difference, that when you in your differential analysis you take care of how that wires are getting transposed, right. So I think it will be, again I will repeat this point in our analysis. So it says that, so now you come to this point. So we wish to combine those propagation ratios for which the input XOR of a differential in any round is equal to the output XOR of the last round differential. Okay. To be precise, the output XOR is actually the permuted XOR of the last round differential. Okay. So that is what I said, and I will again repeat this in our example. Okay. So the prop ratios are assumed. Okay. So another assumption that we make is that our prop ratios, that is the individual prop ratios, are actually independent. Okay. So this is exactly similar to the assumption behind the piling up lemma. So again this comes from the fact that my key scheduling is supposed to provide me independent keys for each round. Okay. And if it does so, then after this XORing you get independent random variables. Okay. So therefore you can assume fairly that the prop ratios are independent. Okay. So therefore you can actually multiply the corresponding prop ratios. Okay. So now you see a real life example, and I think example is always important in these cases. Okay. So you see that in your, so you see that we have targeted some S box, like maybe this S box. So you observe the arrows again. Okay. So you observe this arrow, and this arrow. So what does it mean? That we have set the input differential to certain value. Okay. So if there are no arrows, that means my differential is actually equal to 0. Okay. So you have basically disturbed these points. So immediately if you have disturbed these points, you see that this key XORing does not change the differential. So it just passes these differentials, right. Then what happens is that this S box produces some output, right. So here you can actually have lot of possible outputs. Okay. So but what the attacker does is that from the table he says that, okay, if this be the input differential, then there is a larger probability of this particular differential to occur as an output. Okay. So for example here we have set this as a 1 0 1 1. So it is expected that in the output you will have say 0 0 1 0 as an output. Okay. So that was the larger number of, that is occurring for the larger number of cases, right. So this, now you see, because of the transposition, this, the disturbed bit is this one, right. So this one is the disturbed bit. So where does it go? It goes to this particular point. Okay. So and it actually makes this S box disturbed, right. So what happens to the output of this S box? Again you have set the input to say 0 1 0 0, and again from the table you find out which output differential is more probable. Okay. And then you observe that, okay, so in this case for example 0 1 1 0 is more probable, and you find out where does this go. This bit goes here, this bit goes here. So therefore now two S boxes are getting disturbed, right. And similarly you obtain the corresponding expected output differential here. Okay. So finally you see that in the cipher text, this S box and this S box, in the final round this S box and this S box are getting disturbed, right. So now I am interested in finding out, if I set my input differential to this value and I expect that my output differential is this value, what is the corresponding probability for that? Okay. So what I do for that is very simple. I take the individual probabilities, and assuming that fact that all of them are independent, I multiply the probabilities. Okay. So that is the broad idea. So now let's see the little bit more details. Okay. So you see that here, if I set this value to this, then your prop ratio is half. Why? Now it was equal to 8 by 16, right. So it's equal to half. Similarly for the tables you can obtain these values also. Okay. So they are 3 by 8, 3 by 8 and 3 by 8. Okay. So you see that, so it's exactly the same way as, I mean you can see that why I am interested in these differentials. Okay. So that is precisely exactly the same as I told you, like you have to take care of these differentials and also the transposition of the wires. Okay. So finally you see that your output differential which you are expecting here, or the resultant prop ratio, is obtained as this. Your input is 4 zeros followed by 1 0 1 1 followed by all zeros. Okay. And what is the differential here? It is 4 zeros 0 1 So you observe here actually, okay, here. So it's 0 0 0 0, then you have got 0 1 0 1, okay, and then you have got 0 1 0 1, and then you have got 4 zeros, okay. So I am finding out if I set my input differential to this value and output differential is expected to be this value, what is the corresponding propagation ratio for this big differential, okay. In order to do that, I multiply these probabilities, okay, because all of them has to hold simultaneously, right. All the events has to hold simultaneously, okay. So therefore, if I assume that all these events or all these prop ratios are independent, then I can multiply them, right. So if I multiply them, then I obtain, for example, half into 3 by 8 whole cube, and I obtain 27 divided by 1024, okay. So that is my probability of this particular difference occurring, right. So now what we do is that we obtain the differential of a 3-round approximation of the cipher, right. So is this part clear to us till this part? So now we obtain the differential for 3 rounds, that is 4 minus 1 3 rounds. So we have got x dash is equal to this, that is 4 zeros, 1 0, 1 1 and 4 zeros, and therefore you see that V3 dash. So what was V3 dash? V3 dash was this particular location, right. So therefore this is the differential at this location. So you will see that V3 dash was equal to this value, that is 4 zeros, 0 1 0 0, 0 1 0 1 and 4 zeros, okay, and this probability is actually equal to 27 by 1024, okay. So also note that the key has got no effect on the XOR V3 dash, and thus we have actually V3 dash equal to U4 dash, okay. So therefore it passes. Hence it follows that if x dash, if you set the value of x dash to this, then U4 dash's expectation is this with a probability of 27 by 1024, okay. So note that U4 dash is the input differential at the input of the last round S box. That is what my objective was, right. So I have actually found out an expected differential at this location, okay. So you see that it is equal to 0 0 0 0, 0 1 1 0, then 0 0 0 and again 0 1 1 0, okay. So that is my corresponding output differential, 0 0 0 0 1 1 0, all 4 zeros, and so in this case it is told to be at this point. So you can see that if I propagate that to the output, I can obtain similarly the differential, okay. So that is quite straightforward, okay. So therefore this is this value correspondingly. So you have got 4 zeros, 0 1 1 0, 4 zeros and 0 1 1 0, and your probability is of this occurring is 27 by 1024, okay. So now the real attack. So therefore we have done our our analysis, and what we do is that suppose you take large number of possible plain texts, okay, with keeping in mind that your input XOR is this. So you set this input XOR to this and you take large number of possible plain texts, okay. So in this case we have taken 5000 plain texts, and then what you do is that you obtain the corresponding cipher texts, okay, and you guess the last round key. So now you see that like your linear attack, we needed, so here also you don't require to guess the entire key, you require to guess only these 4 bits and these 4 bits, right. So therefore in your linear attack also we had, if you remember, we had guessed only this part of the key, okay. So if your total complexity of doing the brute force complexity of doing the attack would have been 2 power 16, right, because there are 4 4 4 and 4, but in this case you are just guessing only this part and this part. So how many possible guesses are there? 2 by 8, that is 256, okay. So therefore you are guessing only 256 keys, and what you do is that from the cipher text you go back and you check whether the differential meets the expected value or not, okay. And similarly you do frequency analysis for all the possible keys, okay. It is expected that the correct key will actually give you larger number of probability, will have the highest frequency in the table, okay. So what you do is that you guess the key. Note that you just need to guess 8 bits of the key, okay, and what you do is that you decrypt the last round and verify whether the differential at the input of the last round S box is actually equal to 4 zeros 0 1 1 0, 4 zeros 0 1 1 0, okay. So now you make a frequency table for the keys, right. So what you do is that you make a frequency table for the keys, and if you make a table, this is how a sample table would maybe look like. So you see that we have guessed four keys here and 4 keys here. So you see that 24 was the actual key, okay. So therefore assume that believe that 24 was the actual key, and the probability of that occurring is actually equal to 0.0244, whereas the others has got lesser probability than that, okay. So from this observation we can conclude that 24 is the correct key with a prop ratio of around 27 by 1024, which is actually equal to 0.0264, and you see that it matches fairly with your observed value, which is close to the experimental value of 0.0244, okay. So you can immediately understand that since this is a statistical analysis, doing one plain text, 2 plain text, 3 plain text, okay, it will become more and more close to your actual expected value if you take large number of plain texts, right. So therefore you have to take large number of plain text. So you see that in this case we have been able to do the attack with only 5,000 cases, okay. So you have to keep on doing that until and unless you find that there is a significant key, there is a key which essentially is goes close to the expected value, okay. So the idea is that you have to ensure that you take large number of texts, and then only you can confirm that this particular key is correct, right. So that is the broad idea behind the differential attack. So therefore immediately when we think of attacks, we also should think about immunity, right, because we are essentially not bad people, right, we are good people. So therefore we should think about how to make our cipher strong, right. So therefore the idea is essentially it boils down to the fact that how do I make the S box good, right, that is the central idea. So in this particular case, when I am thinking about how to make it immune against differential cryptanalysis, I have to build the S box with as much uniform distribution as I can, right. So you can see that there are some papers which talks about uniform mappings, okay. So there was a paper by Nyberg which I told you in context to I think in context to AES design. So that paper essentially talks about many such transformations and reflects upon the point of various properties which those mappings has, okay, and which can be probably used as cryptographic mappings, okay. So one of them was the inverse function in finite field, okay, which was adopted by Rindal designers and made the and what works as the AES box, okay, what works central to the AES box. So note that the number of pairs of a plain text and cipher text required is roughly inversely proportional to the probability of the differential, okay. So therefore if I observe like my probability is say p, then roughly the number of pairs that will be required will be proportional to 1 by p, okay. So therefore you see that if your probability that you that you obtain is high, then you require lesser number of plain texts, okay. So therefore that is the idea why you require you need to identify those prop ratios which has got a higher values, okay. So only then you can do the attack with smaller number of plain texts, okay. So a low probability of the differential from the point of the attacker, I will try to make the probabilities as small as possible, right. From the point of the designer, I will make the probability as small as possible, okay. Then the attacker will require large number of texts to carry forward the attack, right. So the S boxes are built to ensure that all the differentials have a prop ratio which is less than a bound, okay. So therefore if I can provide as a designer that okay the prop ratios will be lesser than such values, then I am providing an upper bound to these prop ratios, okay. So that is required from the point of, so when I design S boxes, I require to apply combinatorial theory mathematical principles and really provide such kind of upper bounds, okay. So therefore designing S boxes is not so trivial, okay. So therefore you have to take care of lot of combinatorics and other properties, and you will see that there are a lot of trade-offs also. If you can save this, then the other thing will be exposed, okay. So you have got a very small piece of cloth and you have to actually cover a very big space, okay. So therefore we will see some kind of ideas about which are required to design an S box, certain properties which we need to satisfy for when we are talking about the S box construction in our next classes, okay. But for now you can just take a small exercise. So what you can do is that for each of the hit S boxes of the ES, you can compute the bias of say a given random variable which is like this, okay. So you can do that for say at least for some of the S boxes, okay. and you can just try to find out that whether your DES S box was really good or not. Okay, so therefore you can do analysis. So what you can do for this is that maybe you can write a piece of C code, okay, or a MATLAB code through which you can actually evaluate the differential table of the DES S boxes. Okay, and then I leave it to an exercise. You can actually submit reports on that also. I mean, handwritten reports would do that. Among the 8 S boxes, which S box do you think is the most strong? Okay. So some of the books that I have again followed are the same. So again, this tutorial is very good, so you can follow this tutorial. Okay, so therefore this clears lot of doubts which generally appears in when you see this kind of attack for the first time. Okay. So in our next test topic, we will talk about some other cryptanalytic methods. Okay, so these cryptanalysis methods means that there are large number of cryptanalysis methods which are there, but we will try to understand some of them.